Welcome back. I promise that the next time that I redo these videos that I'm going to get a little more high tech and have some actual better graphics and those kind of things. The problem is right now I'm sort of under the gun trying to get all of this done. Okay, so we're talking about rolling a pair of dice, and I want to bring in a demo right here, and this is found, I just did a search for rolling dice central limit, and the central limit theorem, the CLT, is a very important theorem, and we're going to actually see that. We'll actually use it some in the next chapter even more than in this chapter, but it sort of fits right now because we're talking about rolling these dice. Okay, so what I'm going to do is I'm going to roll the dice. I'm going to roll one die. I'm going to actually roll two die. And the number of trials, let's roll it 10,000 times. And so I'm going to roll it. Okay, now you can see that stair-step design that I tried to draw. Let's kick this up to 10,000 times, and let's roll it 2 times. Okay, let's do it again. So you see that it almost comes out to be that stair-step design. 7 is the most common. Okay, now I'm going to kick up the number of dice to 5, and let's just go ahead and skip to the chase and roll it 10,000 times. Let's do it again. You see, what's happening here is this is approaching a normal curve, a normal bell-shaped curve. And that's just an example of the central limit theorem, which we're going to find is a very important theorem in statistics. I said that already. I can't emphasize that. But it's going to say that these natural situations, like rolling the dice and those kind of things, if we do them often and often enough, the results are going to approach a normal distribution. And so that's a real important thing that we're going to see. Okay, so let's go back to the video and pick up from where we left off. Another type of question that will be covered in this chapter, and let's just look at it right quick. A person buys a lottery ticket for $2. There's a 1 out of 1,000 chance of winning $50 and a 1 out of 1,000,000 chance of winning $500,000. What's the expected value of each ticket? One of the things that I want you to understand is that there's a difference between, statistically, we use the word success and failure. For the person who buys a ticket, the success would be that they win the $50,000. That would be a success. However, that's also a failure for the person that's selling the ticket. So, a success for one, it's a failure for the other. A win for one team is a loss for the other team. So statistically, the terms success and failure, they don't mean what they normally mean in the common language that we often use. And so you'll hear us talk about these, and you may hear us say that that's a success, but you say, well, wait a second, that's not a success, that's really just a failure. But anyway, so however they want to, you want to look at that. So let's see, he buys a ticket for $2, and there's a 0.001 chance of winning $50. So you multiply that out, and that means that it has a value of a nickel. Okay, and then there's a 1 in a million chance, and you want to multiply that by your $50,000, and you can see that that also has a chance of a value of a nickel. So basically what the person is doing when they're buying that ticket is they're spending $2 for a chance for something. They're spending $2 for something that has an actual value of a dime. So that's not really a very good gamble, I guess you'd say. Okay, let's look at another question here. Use the binomial probability formula to find this probability of getting exactly 3 correct answers when random guesses are made for 4 multiple choice questions. Find P of 3, given that n is equal to 4, P is equal to 25, and Q is equal to 0.75. This is given in the book. I mean, this information is given in the book. I just wanted to give you the formula. It's going to be the combination of 4 questions, and you get 3 of them right, times 0.25 raised to the third times 0.75 raised to the first. And so when you multiply that out, this turns into be 4 factorial over 3 factorial, 1 factorial, and times, so that this term becomes 4 factorial over 3 factorial. You cancel terms out. This turns out to be a 4. So you multiply 4 times all these probabilities here, and you get 0.47. Wrong. 0.047. Sorry about that. But so that's less than the 5%. So so it would be considered to be a rare event. Remember that in probability, we have our normal distribution, for example, and things that are 2 standard deviations away from the mean out here that occur out here in the tails. There's 0.025 here and 0.025 here for a total of 0.05. We generally consider those to be rare when they're 2 standard deviations away from the mean. Out of time. Hope this has been helpful to you. Thanks. Okay, I've already picked up a couple of things that I want to talk about, so I'm going to end this video since I've just got 10 minutes on YouTube to show it, and then I'm going to come back with a third one in just a second. So hang on just a minute.